Namaskar students, welcome again to Essential Electricals. In today's lecture, we are going to study about the string efficiency and also the voltage distribution among the suspension type insulator, and also we are going to discuss about the different method for improving the value of string efficiency. So if you haven't subscribed my channel, please go and subscribe it and feel free to give the thumbs up to this video. So let's get this lecture started. So the first thing that we are going to discuss is the potential distribution over suspension type insulator string. Now, in previous lecture, I told you that when the voltage is greater than or equal to 33 kV, pin type insulator is no more useful. So in that case, we have to use suspension type insulator. Okay, so that video, if you haven't seen, the link of that video will be right here in the I button, or also it can be available in the description. So you go and click on that video and go and watch the different types of insulator, then come back and watch the string efficiency. Okay, so the when voltage level is beyond 33 kV, we have to use the suspension type insulator. So here you can see that this is your tower, the body of the tower, or we can say this is nothing but the cross arm. Okay, and this is nothing but your suspension type insulator where three discs are connected. Okay, this is disc number 1, disc 2 and disc 3. Now you know that this point is connected with the ground because this is the cross arm which is connected to the ground, and our live conductor will pass through right here. So this is at the terminal voltage, highest voltage level, and this terminal at the ground potential. Okay, so the potential difference between this point and this point will be V if the line voltage is V. Okay, so in that case the voltage distribution will be V1, V2, V3 in case of disk 1, 2, 3 respectively. Okay, now generally these discs are so designed so the voltage level will be 11 kV, or in case of ultra high voltage or the extra high voltage transmission line, the voltage level for this kind of insulator is 11 kV or 15 kV. Okay, so this kind of discs are made of porcelain, and these are can be connected in series with the help of metal link. So here you can see all these things, three discs are connected in series with the help of a metal ring. Okay, so from due to this metal ring, this insulators behave like a capacitor. So in that case, this is also behaves like a capacitor, this disc is also behaves like a capacitor, and this also behaves like a capacitor. So three capacitors are connected in series. Okay, so it will look something like this. So we know that the total voltage is V, and each disc have the same characteristics. That is why the capacitance, the value of capacitance also going to be same. So here you can see C and C are connected in series. Obviously these are connected in series, that is why the current through this capacitor also going to be same, that is I. So if we write the equation using Ohm's law, that V is nothing but is equal to I multiply by XC. Okay, so we can write V is equal to I into XC, and we know that these three capacitors are connected in series, so the current through this capacitor is going to be same. So this is not going to change. Same, the value of C is also same, so this also not going to be changed. So the V will be same. So we can write V by 3, V by 3 and V by 3. So total V will be divided into V by 3, V by 3, V by 3. Obviously because these are connected in series and each value of C is also same. But when we talk about the practical application, because in practice this is all the theoretical content, but in actual case this will not going to be like that. Okay, because there will be some tower body obviously which is also at ground level, and there will be some shunt capacitance due to this capacitive your we can say the tower body and the your insulator. Okay, there will be some shunt capacitance between the insulator and the tower body. Okay, your tower body will be something like here. Okay, so there will be capacitance between these points. Okay, so that we have to consider. So this capacitance is also known as mutual capacitance or the self capacitance, and this is known as a shunt capacitance. So here you can see in this figure, so this C and C, but also here you can notice C1 and C1. Now all this value will be same. Okay, now the current which is going to flow from this was I in first case, but now it is I1, I2 and I3 in each succession. Okay, because here that will be a current I3 is flowing, and that is why this is I3, and then if you apply KCL you will get the current small I2 and now capital I2 in here, small I1 and capital I1 in this branches. Okay, now due to this the voltage distribution among the disks will not going to be the same. Okay, so here the voltage across this disk is V3, here it is V2, here it is V1. Okay, now the initially current is very high, and that is going to decrease as we are moving towards the cross arm. So obviously your voltage V3 will be maximum, V2 will be lesser than V3, and V1 will be lesser than V2. So we can say that V3 is greater than V2 is greater than V1. Same we can say for your current. So I3 will be maximum, I3 is greater than I2 is greater than I1. Why? So due to this shunt capacitance, our voltage distribution is now unequal. Okay, because due to shunt capacitance there will be some flow of current in this branch, and that is why there will be voltage drop. Okay, now let us discuss about the potential distribution first. So this is what the theoretical part. If we talk about mathematical representation of what we have discussed up till now, let us discuss that. So the voltage impressed on the string of suspension insulator does not distribute itself uniformly across the individual disk due to the presence of shunt capacitance. So we have seen right here that all the voltage across disk is different in case of the shunt capacitance. Okay. The second thing is the disk nearest to the conductor has the maximum voltage across it. As we move towards the cross arm, the voltage across each disk goes on decreasing. Obviously, so let's say again this is disk 1, disk 2 and disk 3. So voltage across this disk will be maximum and this will be minimum. Okay, so as we move towards the cross arm, so let's say my cross arm is right here. So as we move towards the cross arm, voltage across each disk goes on decreasing. So let's say your V3 will be maximum and V1 will be minimum. The unit nearest to the conductor is under maximum electrical stress and is likely to be punctured. So obviously the conductor is right here. So the maximum electric stress will be filled at disk 1. So obviously it is likely to be punctured. Okay, so already I have mentioned that it is generally designed for 11 kV. So if the voltage stress is beyond 11 kV, in that case this disk may punctured, and subsequently all the disks get punctured. Okay, so therefore it must be provided to equalize the potential across each unit. Okay, so that V1, V2 and V3 should be equal. So that is our main task, obviously. In case of, if we talk about the DC voltage, the voltage across such each unit would be the same. It is because the insulator capacitance are ineffective for DC. So obviously in case of DC we don't have to worry about the capacitance, so the voltage distribution across the string will be same. Okay, so this is the disadvantage in case of DC system, but when we are dealing with AC we have to make sure that V1, V2 and V3 are equal. Okay, so that is why the string efficiency come into the picture. Okay, now let us discuss what is the string efficiency, because if the voltage distribution is unequal, in that case under maximum electrical stress this disk is likely to be punctured. Okay, and one by one all this disk is going to be punctured, so that is not the desirable condition. So what we can do, we can maintain this voltage across at same level. Okay, so it can be done with using the understanding of string efficiency. Now let us discuss what is string efficiency. So string efficiency, mathematically it can be represented as voltage across the string divided by N multiplied by voltage across the disk which is nearest to the conductor. Okay, where N is nothing but the number of disks in string. So let us take one example. So let's say my string efficiency N is equal to voltage across the string. So in previous slides we have discussed that the voltage across the entire string is, let's say, V. Okay, and the number of disks is, let's say I am having 3 disks. Okay, voltage across the disk nearest to the conductor. So let's say if we talk about this first case, when we are ignoring the effect of shunt capacitance, so the voltage is V by 3 at all the capacitance. So in that case we can write here V by 3. So that's 3, and this 3 will be cancelled out, this v and this will be cancelled out. So our this will multiply by 100 because we want in percentage. So my string efficiency will be 100 percentage. Okay, when the voltage distribution along the disk will be equal. Okay, so this is the ideal case, but in practical case we always have to consider the effect of shunt capacitance. Okay, so your shunt, due to the shunt capacitance, this value will be different, and this value is higher, obviously your efficiency will be lower. Okay, so we have to make sure this value is should be close to v by 3. So in case of 3, okay, in case of when the disk is 3, if the disk is 5, that should be v by 5. Okay, so in such a way we have to make sure that our efficiency should be close to 100%. Okay, so the greater the string efficiency, the more uniform the voltage distribution there in case of suspension type insulator. Okay, so this is all about the string efficiency. Now let us discuss that. Let's say we are having again the same situation. This three insulating discs are there, the conductor is here, and all three shunt capacitance is having the value C1, your self capacitance having the value C. And if you look at this formula, that let's suppose self capacitance is C and shunt capacitance is C1, and the relationship between this C1 and C is C1 is equal to K times C. Okay, so here we have taken one coefficient K. Now starting from the cross arm, or we can say from the tower, the voltage across your V1, V2 and V3 is shown. Okay, so V is divided into V1, V2, V3. Obviously the value of V3 is going to be higher than V2, and V2 is higher than V1. Now if you want to apply the KCL at this point, you will get this I1 plus capital I1 is equal to I2. So at this point incoming current is I2 is equal to capital I1 plus small I1, because we want to find out the relationship between V1, V2 and V3. Okay, so now if you put the value of I2, I1 and I1 in this equation, you will have the relationship between V1 and V2, that is known as V2 is equal to V1 1 plus K. Okay, so because here it is the C1, C is there and C is also there, so if you write for I2, I1 and I1, you will get in terms of V2 and V1. Okay, you have to put the value. I am not going to do that, but you can easily. Okay. Same way, if you apply the KCL at this point, you will have the same equation, that incoming current is I3 is equal to outgoing current small I2 plus capital I2. Okay, and if you put the value of I2, both this I2 small and capital and I3, you will have the equation in form of V3 and V2. Okay, and obviously we have that V2 in form of V1. So if you put the value of V2 in this equation, you will have the relation between V3 and V1. Okay, now these the two equations are important. So from this we can write that V1 divided by 1 is equal to V2 divided by 1 plus K is equal to V3 divided by this should be 1 plus 3K plus K square, because right here it is 1 plus 3K plus K square. Okay, so we can write this V3, and we can take this term in denominator. This term in denominator we can write V1 by 1, V2 by 1 plus K, V3 by 1 plus 3K plus K square. Okay, so that should be plus right here. Now voltage between the conductor and earth, or we can say your conductor and this tower body or the cross arm, is total V, that is equal to V1 plus V2 plus V3. So if we are taking V1 as a reference, then we can write V1 plus V2 is equal to V1 into 1 plus K, and V3 is equal to V1 into 1 plus 3K plus K square. And if you just simplify this equation, you will get V1 3 plus 4K plus K square. If you take the ratio, you will have V1 is equal to V divided by 1 plus K 3 plus K. So you have to simplify this equation too. Okay, so that will be 1 plus K and multiply by 3 plus K. So yeah, you can write V1 is equal to V2 divided by 1 plus K, V3 divided by 1 plus 3K plus K square is equal to V divided by 1 plus K into 3 plus K. So if you have the value of your total V and this K factor, you will have the value of V1, V2 and V3. Okay, so let me discuss some of the things related to string efficiency. So let us take for example K is equal to 0.2. then we get the value of V2 is equal to 1.2, because we know that here, let me show you the formula. So V2 is equal to 1 plus K into V1. Okay, so if you put the value of K in this equation, V2 is equal to V1 1 plus K. If you put the value of K right here, that is 0.2, 1 plus 0.2 will be 1.2, so your V2 will be 1.2 into V1. Same way your V3 will be 1.64 into V1, because that will be V3 is equal to V1 1 plus 3K plus K square. Okay, so if you put the value of K, you will get 1.64 into V1. So this clearly shows that the disk which is nearest to the conductor, which is V3, has the maximum voltage across it, and the voltage across the other disk decreasing progressively as the cross arm is approached. So you can see this V3 is greater than V2, and V2 is obviously greater than V1, because V2 is 1.2 times V1. Okay, so the greater the value of K, it means K is nothing but, because we know that Kc is equal to C1, because in previous slide we have taken this. Let me show you. We show that here C1 is equal to K into C, so K will be C1 by C. Okay, so let me come to the point. So K is equal to C1 by C. Okay, so if the greater the value of K, the more non-uniform is the voltage across the disk, and lesser the value of string efficiency. So our task is to maintain the value of K as small as possible. Okay, because the more the value of C, the more non-uniform the voltage distribution, and the string efficiency will be lesser. So the unequally in voltage distribution increase with the increase of number of disk, and hence the shorter string has more efficiency than the larger one. Okay, so when the number of n, which is nothing but number of disk, if n is increasing, obviously your string efficiency will going to decrease, because the proportion between your number of disk and the efficiency is inversely proportional to each other. So if n increases, obviously your string efficiency will going to decrease. Okay, so in case of 3 disk insulator, the string efficiency can be more in compared to the 5 or 6 disk. Okay, so in that way we are going to deal with this. So our task is to maintain the voltage distribution among the disk will be as equal as possible. Okay, now how we can do this? Because the string in a suspension type insulator, the shunt capacitance will also always going to be there, and due to this we'll never able to get your V1 is equal to V2 is equal to V3. So how, what we can do to maintain your V1 is equal to V2 is equal to V3? Because this is the only way to neglect the effect of your shunt capacitance. Okay, and that is why if you just neglect this effect of C1, or and if you, in order to make V1 is equal to V2 is equal to V3, so we can make our string efficiency nearest to the 100%. So how we can do this? So these are some of the methods that we can use. The first one is by using the longer cross arm. Now let us discuss these methods. Second is by grading of insulators, and third is by using a guard ring. Now let us briefly discuss about by using the longer cross arm. So let's say this is the tower, and these are 1, 2 and 3 insulator. Here is your conductor. So if we are using longer cross arm, in that case the value of shunt capacitance is very small. So your C1 will be very small in case of longer cross arm. Okay, if C1 is less, obviously your so not V1 but your current, sorry, your small current I1 which is going to flow in this branch will be less. Okay, so in that case we can write that I1 is nearly equal to I2 is nearly equal to current I3, and in that case your all three disks are connected in series, so your V1 which is nearly equal to V2 which is nearly equal to V3. So from this we can say our string efficiency is nearly 100%. Okay, so if we increase this length of cross arm, the distance between your disk and tower body will be larger, so there will be negligible value of shunt capacitance. Obviously, in that case we can improve the string efficiency. But this is not economical because by making the longer cross arm, the we can say the requirement of cross arm will be more, and obviously it will require the heavy structure of tower, okay, to withstand such kind of heavy mechanical load, and that will increase our cost, obviously. So that will be not useful method for improving the string efficiency. We cannot use this. The second is by grading of insulator. Okay, so again here I have to make 1 plus 3k. So here you can see v1, v2 and the relationship between v3. Okay, in case of when the shunt capacitance is there. Okay, so by grading insulator in such a way that whatever the disk which is nearest to the conductor which has higher voltage level. Okay, so let's say this disk is the nearest to the conductor, so the grading of insulator is doing in such a way that these two disks are having higher voltage level. So this disk is having higher voltage level than this is having higher voltage level than this. In such a way the grading should be done, so we can having the voltage distribution in proper manner, so we can improve the string efficiency. Okay, but this is also not economical because if some of the insulators, or we can say one of the insulators is punctured, in that case we have to replace it by only the specific we can say the specific types of insulator. We cannot replace by let's say this is insulator number 1, insulator number 3, insulator number 1, 2 and 3. So if my number 2 insulator is punctured, in that case I cannot replace 2 with 3. Okay, so in that way the maintenance will be not easy. Okay, so we cannot also use this kind of grading of insulator to maintain the string efficiency better. The third method is by using a guard ring. So here you can see in this figure we are adding guard ring at this point, and due to this what happened that the charging current will flow from this path. Okay, so here you can see there will be some capacitance, and due to this the charging current will flow. So whatever the current which is going in this branch, that is compensated by the I2 dash. So this current is going I2, so I2 dash will be compensated by at this point, so this will be again I2. So current through this branch is going to be same irrespective whatever the shunt capacitance is there. So guard ring will compensate the rest of the current, and that is why the voltage distribution among the disk will be same, and that is why the transmission efficiency N will be improved. Okay, so these three methods, and most of the case by using guard ring we are improving the value of your string efficiency. Okay, so this is only the briefly introduction of the methods of improving string efficiency. In future we will going to make a dedicated video on the improving the string efficiency. Okay, so I think this is all about the string efficiency that you should have to know about, and from next lecture we are going to start some new topic. Okay, so yes, this is all about today's lecture. Thank you so much. See you guys next time.